So, welcome you all for the session of Theory of Computation. Now we'll see minimization of DFA. So, minimization of DFA is required to obtain the minimal version of any DFA which consists of the minimum number of set of states possible. So, the DFA is minimized when the two different states are said to be equivalent. Then, how do you find the equivalent states? So, two states A and B are said to be equivalent if the transition function of A on X tends to final state and a transition function of B comma X tends to final state, or transition function of A comma X tends to non-final state and transition function of B comma X tends to non-final state, here where X is an input symbol. So this will be clear when you solve the particular problem, right? So here minimize the following DFA. This problem is used to solve a minimization of DFA. So when the problem has given, you have to look at this problem and you will see what are all the states which is unreachable in a particular state diagram, right? Here A is a starting state and B. See here B. So B is reached from A, right? Okay. And C, so A via B, C is reached. And now D. Check D is reachable from any of the states via a particular state. A, B, actually in D there is no incoming edges, right? So incoming arrow marks, right? So D is an unreachable state. So whenever you find an unreachable state in a particular DFA, it should be avoided, right? After that you're having E. So how the E is reached? So using initial state A and F will have right A, B, G, and via using this G you will get an E, right? It's an reachable one. Next F, you will have the initial state from A to F, and G, A, B, G, and H you will have how do you reach it? Using E you will reach a H. The only state here unreachable is D, and it should be eliminated. So the first step here is to eliminate the unreachable state over here, right? Okay. For this we need to draw a transition table. So after a transition table has been written, the table will be look like this, right? So here you'll have this A on 0, it will going to B, and 1 and going to F, and B on 0 it is going to G, and 1 C, and C on 0 A, and C on 1 C, and D will have the state but will not will have to eliminate it because D is an unreachable state, and E on 0 H, and E on 1 F, and F on 0 C, and F on 1 G, and G on 0 G, and G on 1 E, and H on 0 H on 0 G, and H on 1 C, right? Next we'll see a zero equivalence. So how do you see the equivalence state? For zero equivalence, we will separate the two different states. One is set of non-final state and another one is set of final state. So here C is a final state, right? So here C is a final state and A is an initial state. So I just separate it like this. So this is a set of final state and this is set of non-final state. After that you're having a one equivalence. So in one equivalence, here we'll need to check A and B are one equivalent or not. How do you check it? So just look this transition table. A and B on 0, it is retained the same state. Okay, on 1 for A and B, just look at this A and B. On 1 it is going to two different states. One is in this one, and another B going to C, and A going to F. These are from the two different states. So obviously it is a A and B are not one equivalent, so just separate over here, right? So whenever you will have this final state, you just keep over here. You should not be splitted anymore, so it should never be touched, right? So this C never be touched. After that you have this one. After that you will going for AE. So you have to find the equivalence of AE. What is the equivalence of AE? Just look at this here for A, B and H. So whenever you check the result, you have to look at the zero equivalence, previous result. If you are processed in one equivalence, you have to look at the result on zero equivalence. If you are in two equivalence, you have to look at the result on one equivalence, right? So now we have to make a comparison AE. So AE equivalence, right? Whether we have to check one equivalence on AE, right? So for AE, it is written on a same state, right? Okay. And on 1, it is on a same state. So A and E are equal, right? After that, we will have this AEF, right? We will have to compare AEF. So whenever A and F on 0, right? So what will happen? It is on two different sets. Why? Because F is on 0, it is going to C, and A is on 0, it is going to B. So it is two different states. Then we'll check for whether it is equivalence to B, right? So we'll check for B and F, right? Okay. So B and F. So for B and F on 0, GC, right? It is also separated. So we'll have F. After that, you will look for G, right? A and G. A and G, right? Take any one of this A and G. So using this, you have to check for A and G. So B on 0, it is going for BG. So it is in the same set. And on 1, it is going for F and E. So it is also in the same set. So A, E, G, right? So these three are one equivalence. Right. So one more thing is available, right? Sorry. So one more thing is available. We are left over H, right? Next one is H, right? We'll have to check A and H. So on 0, where it will go? BG. On 1, it is going from a different sets, right? So we'll check for H in the set of B. So we'll check for B and H. So it is going for the same set G, and it is going for the same set. So B and H are equivalent for this set, right? After that, we'll have anything left out? No. Just close it here also. So 1, 2, 3, 4, 5, 6, 7. Okay. So this is this two equivalence, one equivalence. Now we are going to find a two equivalence, right? Two equivalence. So two equivalence. So whenever you find two equivalence, whatever set of states where you have to left out in a one equivalence, which is in a single state, right? Which means it cannot be splitted. So you just write in a first thing, and you have to check this equivalence. So you should not touch any more on C and F, right? So you should already it is splitted up, so we cannot split it further. So that's why you'll write on a first step as an initial one in a two equivalence partition, right? Now we'll have to check for A and E, right? So A and E, and A and E on 0. Whenever we compare for two equivalence, we will have to check the result on one equivalence, right? So for A and E, where the set will go? BH. Okay, it is in the same set. And on 1, this one side. Okay, then A, E, or N, same thing. Next, A and G, right? A and G. So it is going to be G. So B and G are different sets. So we'll have to separate it, right? G. Okay, fine. And now you're having BH. So we'll have a BH. You have to check this B and H. On 0, G, it retains G, and on H, G. So both are in the same set, and for 1, they both are in the same set, right? So we'll have B and H are in a same state, right? So now we'll go for an three-equivalence. So whenever you're having you get a single set, just refer it a initial. You have to write in an initial thing, right? Then only next we'll see for AE, right? Okay, AE. Just compare it. AE. You have to compare the result with the two equivalence. Now you are finding three equivalence. So AE, for AE you have to on 0 it is going to BH, the set in the same set, and on 1 it is going for F, the same set, right? So AE is a three equivalent set. After that you will have a BH. So when you are comparing BH, so it is on 0 it is going to G, a same set. On 1 it is going to C, so same set. So it can also be not split, right? This is three equivalent. So whenever the two equivalent sets are equal, here see here 3 C F A E G B H, and similarly you are having C F G A E B H. So furthermore we cannot be proceed. So this until this step we can stop over here. So we cannot be proceed further because two equivalence and three equivalent sets are same only. If you further move on the same next step, the same result will be obtained, right? For this, now we'll have this transition table, right? So look at the transition table over here. Transition table. So now so this is the final case for our transition table. Here A and E states are equivalent and B and H states are equivalent. So initially we are having 3 4 5 6 7 8 states, but now 3 4 5 only 5 states. We have minimized our DFA. So initially we are having see here, initially we are having 8 states. Compare this diagram, right? So initially we are having 8 states, but now after minimization, after the equivalence partition, we will have the state of 5. So see, and we'll have this transition table, right? On 0, on 1. So this is whenever you are having A, it should be written as AE. Right, so A and E are equivalent. Then E, we have to eliminate this E state. So whenever we are having B and H are equivalent, you have to delete this H equivalent, right? Okay, fine. AE, on AE, just look at this table AE, where it will go BF, right? So B. So whenever you are writing B, it is equivalently known as BH. So it is replaced by BH and BH, and for this F, it is F only. Okay, fine. And the next one is B, right? Whenever you are writing a B, it has to be written as BH, and BH only G is a single state over here, and you are having C. So right, as usual, G and C. Right, after that you will have a C. So C, for C you have to write an AE. Wherever A present, you have to write it as AE, and it is C, right? So something like this. Okay, after that we have eliminated D state. Now we will have this E, right? So for E we have to eliminate this. Why? Because already we have find AE, right? So E is also eliminated. Next one is F. So F, for F, wherever F comes is going for C and G, right? So replaced by C and G. Okay, after that next we'll have this G. So G is a separate state here. So when G and this after on one transition E, so E is equivalently written as AE, right? Okay, so the final state over here is C, right? Now we have to draw a transition table. So transition diagram, right? Transition diagram. So here a transition diagram. So AH, right? And you're having a BH, and we have F, GC, right? Okay, fine. So G, this is AE, right? Not AH, AE. AE, BH, G, and we'll have F. So this is our final state. C is a final state. So we have to put in a double circle, and for F, right? F is present over here, right? Okay. So this is the start state, and on AE it is going to, on 0 it is going to B, right? On 1 it is going to F. On BH, on 0 it is going to G. On 1 it is going to C. On C, on 0 it is going to AE. On 1 the self state. Okay. On F it is going to C. On 0, on 1 it is going to F. On G it is a self state only on 0. On 1 it is going to A. So this is my minimized DFA transition diagram, right? Thank you for watching this.